Hi there, mathematicians. We are here today to talk about complex numbers in some ways that you may not have seen them before. You have probably used complex numbers with quadratics. You probably think of complex numbers as the ones that have I in them. That's true. Complex numbers, we have raised them to a power, or we've multiplied them, added them, etc. But this time what we're going to talk about is graphing them, finding their absolute value, and then writing them in different forms. So first off, I want to show you how easy it is to graph a complex number. Graphing an absolute value with complex numbers are both very easy, but if you don't know how to do them, then of course they're impossible. So once you know how to do them, it makes it so cool, so clear. Basically, here's the deal. When you have a complex number, a plus bi, and that's standard form with the I part written second, the way we graph it is like this. The a is like your x and the b is like your y. So one way of thinking about it is the real part of the number gets graphed on the horizontal axis, and the imaginary part of the number gets graphed on the vertical axis. So for instance, if we had the point 3 minus 2i, okay, 3 minus 2i, this is a positive 3. That's the real part. So I go 1, 2, 3 on the real axis. The imaginary part, and it's the number in front of the imaginary part, is the negative 2. So on the imaginary axis, I go down 2. The I is implied by the fact that I'm using this axis for that number. So I don't have to do anything special with the I. Just take the number in front of it and represent it as the vertical part of getting to my point, the vertical direction. And so basically it's like graphing this point right here. So 3 to the right, down 2, and there is that point. So that is the point 3 minus 2i. All right, so what about the point, how about negative 2 plus 5i? Okay, negative 2 plus 5i. The real part is negative 2. So I'm going to go 1, 2 to the left. And then positive 5 on the imaginary axis means positive 5 up. 1, 2, 3, 4, 5. So I'm going 2 to the left and up 5. And there is the point, negative 2 plus 5i. So again, you don't have to do anything special with the I. The I is just indicated by the fact that I went up or down that amount. I know that whatever distance up or down I go, that's my I. And whatever distance left or right I go, that's my X. All right, so that's all there is to that. Now, the next thing is finding the absolute value of a complex number. And that looks something like, let's actually take this one. There we go. Just putting absolute value around the whole thing. Okay, so here's the thing. Remember that when we talk about absolute value on the number line, the meaning of absolute value is distance away from 0 or distance away from the origin. Well, so here is my origin. So if I want to know how far this point is from that point, well, I need to know how far I'm going this way. Let's use a different color. How far I'm going this way and how far I'm going this way. I could use the distance formula, but another way of using the distance formula is to think of it just like the Pythagorean theorem. Pythagorean theorem and distance formula pretty much say the same thing. Okay, two different ways of looking at the same thing. So this way it's, here's my negative 2 and here's my 5. And to get this distance, the diagonal, I'm going to do negative 2 squared plus 5 squared and then take the square root. That's this length. So it's exactly like doing the Pythagorean theorem. All right, so negative 2 squared is 4, 5 squared is 25. So the absolute value of negative 2 plus 5i is the square root of 29. And you might sometimes be asked for that as a decimal. You pretty much have to go with however it's asked. If I'm asked for it in exact form, that means leave it like this and just simplify if I can, which I can't here. So let's look at the absolute value of 3 minus 2i. Absolute value of 3 minus 2i. means how far this point is from the origin. So again, I'm going to think like Pythagorean theorem, and I'm going over 3 here and down 2 here. So if I want this distance, I'm going to do square root of 3 squared plus negative 2 squared, which is the square root of 9 plus 4, which is square root of 13. And that's the absolute value of 3 minus 2i. Okay, so again, if we think of a complex number as a plus bi, where a is the real part and b is the coefficient of the imaginary part, then we graph it just like ab. And if we want the absolute value of it, it works like this. Square root of a squared plus b squared, which is what we've done here on all of these, both of these. All right, the I doesn't come into it because remember the I didn't come into the graph, or it does come into the graph, but as the vertical distance. And that's represented here by 5 or here by negative 2. So we don't have to do anything special with the I when we're finding the absolute value. We just take the square root, the square root of this number squared plus this number squared. And that's my answer. Absolute value of a complex number is something that people tend to forget a lot, what they're supposed to do with it. Okay, mainly because there's not a whole lot to it, and this is my opinion. When we go over it quickly and then we're done. And so I feel like it becomes forgettable just because we don't practice it a whole lot. We do a few problems and we say, okay, that's easy enough. For instance, here we go. Absolute value here, that would be the square root of 3 squared plus negative 4 squared, which is 5. So the absolute value of 3 minus 4i is 5. What about the absolute value of just a number? What if it's the absolute value of 6 or the absolute value of 5i? Okay, well, this is the same as 6 plus 0i. So it's just 6. This is the same as 0 plus 5i. That was 5 squared. I didn't really write it that way. And that's just 5. But also, in terms of what it means, it makes sense. Absolute value of positive 6, think about how to graph that. Actually, this graph is getting kind of busy. Let's think about how to graph that, where we have a real number line, or a real axis and an imaginary axis. 6 would be on the real axis. So if we want to know how far that is from 0, well, it's 6 from 0, 0. If we're just going 6 to the right, then the distance here is just 6. And 5i just means up 5. So the distance here is just up 5 is 5. So again, if absolute value is distance away from 0, then if you don't have A and B, it's just your A or just your B. Here I just have an A, here I just have a B. I don't have to do the Pythagorean theorem because I'm on one of the axes there. All right, next, let's look at taking a complex number and writing it in polar form. Okay, write the complex number in polar form is the direction we would read. Okay, to me, the easiest way to think of this is if you already know how to go back and forth between rectangular coordinates and polar coordinates, which is very often you've done that just before you do this. And if I have a complex number, then the rectangular coordinates, and it's basically based on how we graph it, same thing as right here, how the graph works, the rectangular coordinates here are AB. AB is just like XY. Okay, so if I needed to take an xy and write it in polar form, remember that we have r is equal to the square root of x squared plus y squared. So that would be a squared plus b squared. Again, this goes with what we just learned on the graph, because r is our radius, is the distance from 0, 0 out to the point. And theta is the inverse tan of my y over my x, which in this case is b over a. Now, if we didn't believe that that should be true, let's think about it. If this is the point, a plus bi, that means this distance here is a, and this distance here is b. So that's the rectangular way of describing that. Now, the polar way of describing a point's location is how far out from 0, 0 do I go, which is r, and how far or what direction in terms of angle starting at the positive x-axis. So remember, polar coordinates are r and then theta. Rectangular coordinates are just x and y. So if I wanted this r, Pythagorean theorem says I would do the square root of a squared plus b squared. If I want to know what theta is here, basically the angle is opposite over adjacent. I should have drawn it in the first quadrant really here, because this one's a little bit, it seems a little different, but because of the signs, it'll work out fine. Okay, it's kind of like your thetas here. Okay, so let's write 5i in polar form. Well, first thing to me is writing it in rectangular form, realizing that in terms of a and b, this is b, a plus bi. And so that means rectangular form for this point is 0, 5. So my radius is the square root of 0 squared plus 5 squared, which is square root of 25, which is just 5. And my theta is the inverse tan of 5 over 0. And 5 over 0 is undefined. So basically it's asking where, it's kind of like saying the tangent of theta is undefined. And we have to think about where is tangent undefined. Well, this can help us because we know 0, 5 means go 0 to the left and right and up 5. And sure enough, that's where tangent is undefined. Tangent is sine over cosine. And this point, or remember this is, if we were on the unit circle, that would be 0, 1. Okay, so this is really saying 0, 5. We're going up 5. So y over x, sine over cosine, gives you undefined. So this is pi over 2. So my polar form of this number would be just 5 pi over 2. Okay, let's try another one, and this time go from go from complex to polar. Okay, so I just said that we were going to go from complex to polar this time as if we didn't last time. In my defense, I was rattled because I was trying to make the dog stop barking. So I have paused and come back, and we have a happy dog who should not be barking. So let's just do some more of these. Here is 2 minus 2i. So first off, in rectangular form, this is a plus bi. So my a is 2, and my b is negative 2. So if I'm going to write that in polar form, my r is the square root of a squared or x squared plus b squared. So that's 4 plus 4, which is 8. Whoops, still in the radical, which is 2 root 2. So that's what r is. And then my theta is the inverse tan of negative 2 over 2. Okay, so that's the same thing as saying the inverse tan of negative 1. There are two places that a tan has a value of negative 1. So tan is negative 1 right in the middle of the second quadrant and also right in the middle of the fourth quadrant. So I have to think about where this one is. This one is right in the middle. It's to the right and down, so it's right in the middle of the fourth quadrant, which is at 7 pi over 4. So theta equals 7 pi over 4. So you do have to use the rectangular coordinates very frequently to figure out which of a couple of possible values would be the right angle, the correct angle. So there's my answer in polar form. Let's try another one like that. Negative 3 root 3 minus 3i. All right, my radius, and again, this is negative 3 root 3, negative 3 in terms of a and b. So my radius is a squared plus b squared, all under the square root. And this is 9 times 3 is 27. And this is 9. And together that's 36. And my answer is 6. So that's a nice one. Then we have theta is the inverse tan of b over a. That would be the same as if I divide out the 3's, this, which is one of my unit circle values of tan. I like to think with tangent, I always like to think about the fact that this is just the same. I think about what it would be with a 2 under it, because that's how the unit circle values look. So we're thinking about where the sine is 1/2 and the cosine is root 3 over 2. All right, so that happens at pi over 6, but that's not the only place it happens. We could also have, to have a positive tan, I could also have negative and negative. So it could be pi over 6 or it could be 7 pi over 6. So we got to go back over here and look and say, oh yeah, that's going to be 7 pi over 6 because both of these are negative. So it would be in the third quadrant. So in the third quadrant, you have negative root 3 over 2, negative 1/2. And when we put opposite, just like theta, opposite over adjacent, we get 1 over square root of 3. So that is 7 pi over 6, and that's my answer. So my radius, or excuse me, my polar coordinates are radius of 6, and the angle of rotation is 7 pi over 6. All right, next we're going to do a complex number in rectangular form that starts out in polar form. So here's the cool thing, is think back to when we were going from polar to rectangular or rectangular to polar, and we had these little formulas. And again, and I have a video where we talk about how to come up with this. This is not very hard to come up with because cosine is adjacent over hypotenuse. And if we use this picture, any of these pictures that we've been drawing, go back to the very beginning, any of those, and want to talk about our x values and our y values in terms of r and theta, it would be pretty easy to come up with that. So what you see a lot of times for excuse me, complex numbers that are given in polar form and asked for rectangular form is you'll see things like this. Okay, now what this is the same as is this is just like this negative 5 is factored out. So that's kind of like The -5 is the radius, and the pi over 4 is the angle of rotation. Okay, so that's kind of like your r and your theta. So that's why that's considered to be in polar form. Well, if this is x and y then that's basically going to be A and B. So in other words, this is A plus B times I. We can just calculate this. We don't really have to translate it as much as we just simplify it. Cosine of pi over 4 is square root of 2 over 2. So -5 times root 2 over 2 plus, and sine of pi over 4 is also root 2 over 2. So we just get -5 root 2 over 2 plus -5 root 2 over 2i. And sometimes people might like to write the I in front here on top, but it all works pretty well the same. And you also could write this as a minus in the middle instead. Let's try another one like that. Let's do one with degrees. Let's say we have 2 times cosine 60 plus I sine 60. Sorry, you can't see this. I'm getting really bad about leaving that down there. Sorry. Okay, so this is the same idea as 2 cosine 60 plus 2 sine 60 times I. Okay, more barking dog drama. So again, at this point, all we have to do is just calculate this. Just go ahead and simplify this. The cosine of 60 is 1/2, so 2 times 1/2. And the sine of 60 is root 3 over 2, so that. And we have 1 plus root 3i. And that is my polar number in rectangular form. And I think we will call it right here. Thank you for coming. I'm going to have another video after this talking about multiplying complex numbers, talking about raising complex numbers to a power. So feel free to come join me for that one. And thank you so much for watching.